Then here we have to discuss the exercise 4. The question is, given an infinite matrix Aij, ij equal to 1 to infinity, where sigma I equal to 1 to infinity, sigma j equal to 1 to infinity, absolute value of Aij square is less than infinity. Define A from L2 space to L2 by A into sequence x1, x2, etc. is equal to sequence y1, y2, etc. Where Aij into x1, x2, etc. equal to y1, y2, etc. That is yi equal to sigma I equal to 1 to infinity Aij xj. Then here we have to prove that the operator A is a bounded linear operator on the space L2. And also we have to show that norm A square less than or equal to sigma I equal to 1 to infinity, sigma j equal to 1 to infinity, absolute value of Aij square. Then here we have infinite matrix. Then we have to define A from L2 space to L2, and A of x is equal to sequence y1, y2, etc. Then we have to prove that the operator A is a bounded linear operator. Then we have to prove that norm A square is less than or equal to sigma over I, sigma over j, absolute value Aij square. Then we know that A equal to A is an infinite matrix, Aij over Ij equal to 1 to infinity. Then we have to write A is equal to matrix A11, A12, A13, A21, A22, A23, A31, 32, A32, A33, etc. Then we have to then be such that k square is equal to sigma over ij equal to 1 to infinity, absolute value Aij square less than infinity. It is a finite sum. Then we let x is equal to sequence x1, x2, etc. Arbitrarily chosen. This sequence belongs to L2. Then we define an operator A from the space L2 to L2. Then it define A of x equal to sequence y1, y2, etc. We know that here we have to let x is equal to sequence x1, x2, etc. Then we have to put this sequence x1, x2, etc. That is A of sequence x1, x2, etc. equal to sequence y1, y2, etc. Where yi equal to sigma over I equal to 1 to infinity Aij xj for all I belongs to n. Then we have to put summation, and here we have to put summation and squaring both sides. That is sigma over I absolute value yi square is equal to sigma over I modulus sigma j equal to 1 to infinity Aij xj square. Then we have to take the modulus inside. Then equality is less than or equal to, that is sigma over I absolute value yi square is less than or equal to sigma I equal to 1 to infinity, sigma j equal to 1 to infinity, absolute value of aij square into absolute value of xj square. Then we know that the value of k square is sigma ij equal to 1 to infinity, absolute value of aij square. Then we have here there are two summation and absolute value aij square. Then this term will be, we have to write this k square, which means is less than or equal to k square into sigma modulus xj square, which is equal to k square norm x square, which is less than infinity. This is a finite sum. Then we have to put, this is equation number 1. Then A is well defined, also A is linear. Then from one we get and the L2 norm of a of x square less than or equal to k square L2 norm of x square for all x belongs to L2. That is norm a of x is less than or equal to k into L2 norm of x for all x belongs to L2. So that A is bounded and norm A is less than or equal to k. Therefore, we can write A is a bounded linear operator. So we have to prove the first part. In the first part, we have to prove A is a bounded linear operator. Then we have to prove that norm A square is less than or equal to sigma over I, sigma over j, absolute value aij square. Then we have mod yi is less than or equal to sigma j equal to 1 to infinity, absolute value aij xj, which is less than or equal to sigma j equal to 1 to infinity, absolute value of aij square all power 1 by 2 into sigma over I equal to 1 to infinity, absolute value of xj square whole power 1 by 2. For x is equal to sequence x1, x2, etc. Norm ax square is equal to sigma j equal to 1 to infinity, absolute value yi square, which is less than or equal to norm x square sigma over I, sigma over j, absolute value aij square. Then we have to write norm a square is less than or equal to sigma over I, sigma over j, absolute value aij square. Then we have to prove the inequality.